Okay, so in today's lecture, we're going to start with section 3.7, and these are optimization problems. Okay. And the best way to cover this topic is just to go through a bunch of examples. So let's look at an example problem. And suppose the problem is, say, we want to design an open box, okay, having a square base and we're limited to a surface area for our box of, say, 108 inches squared, or 108 square inches. Okay, so then the problem becomes, so what dimensions of this box will produce a box with a maximum volume. Okay, so we need to design a box with a square base, and we're limited to having a surface area of 108 square inches. And among all such boxes, we want a box that has a maximum volume, right? You can think of this type of problem occurring a lot in manufacturing settings. So I always like to draw pictures to kind of help me get my head around what's going on. So here's our open box, right? Okay, and it has a square base. So if it's a square base, then this side is the same length as this side there. Same length there, same length there. So let's just go ahead and call that length maybe X. And then this will also have length X that way. And then the only other dimension we have to worry about is the height. Call it H. Okay. So now we want to pick values for X and H that will maximize the volume of this box. But we're limited to, we have a constraint that we can only have a surface area of 108 square inches. So in order to model this problem with calculus, we need to first write down what equations that we're dealing with. In particular, the volume of a box is going to be important. That's what we want to maximize, right? So the volume of a box is length times width times height, right? But here, the length and the width are the same X. So in this case here, the volume of this box is going to be X squared times H. So far, so good? All right. So that's the equation that we're going to end up optimizing. Okay. And sometimes people refer to this as the primary equation. Okay. So what else do we have that we're working with? This constraint, right? The surface area needs to be at equal 108 square inches. So what is the surface area here for this box, right? So if you just have like just some rectangle, right? The surface area here is just x times y, right? And, yeah. Okay. So of the bottom of this box, right? What's the area of the bottom of that box? It's just x times x, right? So I know that I'm going to have an x times x for that, right? But then I have this side, that side, that side, and that side, right? And that's the total surface area of the box because there's nothing on top, it's open, right? So what is that? That's, well, x times h, right? For this piece. And then here, that's x times h, x times h, x times h, right? For those four sides. So the area is 4 x times h plus the bottom panel. So that'll be the total surface area. And we know that this is going to be equal to 108 inches or square inches. Okay. So this is, your textbook refers to this as the secondary equation. Okay. But I would also call this a constraint. Okay. We need to maximize this subject to this constraint. Also, we know something about the lengths here of x and h, right? We know that they're not going to be negative, right? So we also know that x is greater than or equal to 0, and we know that h is greater than or equal to 0. So to form this in a more formal fashion than your textbook does, I'm going to write out the actual optimization problem in the standard notation that you would see in an optimization course. So our problem is this. We want to maximize x squared times h, where we're choosing variables x and h, such that x squared plus 4x times h is equal to 108 square inches, and x greater than or equal to 0 and h greater than 0. So we're maximizing this function according to x and h such that this constraint holds, this constraint holds, and this constraint holds. So these are each constraints on that optimization problem. In fact, this type of problem is referred to as, so this is constrained optimization.
Why do we write greater than or equal to 0 instead of just greater than 0?
It's true either way, right? It's just standard for me anyhow, to say greater than or equal to 0.
Gotcha.
Okay. Okay, so now how can we solve this? Well, typically what you'll want to do, oh, when I said, I almost forgot that the primary equation, I would call that the objective function. Using the language of optimization, that would be referred to as the objective function. But your textbook uses primary equation, secondary equation. But I really would like to emphasize, you're trying to maximize the objective subject to the constraints on that objective. Okay, so when solving this problem for us, since we only know how to deal with optimizing functions of a single variable, notice that there's two variables here. So I would say the first thing that we should do is answer the following question. Can we write the objective function as a function of one variable? Okay. Because right now it's a function of two variables, x and h, and we don't know how to do that in Cal 1, right? So it turns out that we can if we use this secondary equation here. So in particular, we can say, notice that this equation here implies that h is equal to 108 square inches minus x squared all over 4x. Right, if we solve for h with that constraint, we can write h in terms of x, okay? So really, what does our objective function become when we do that? So this becomes if I substitute in for h, what in terms of x. So this becomes, what is that? So I have a 4 there. So this becomes 27 inches squared. Where did I write it? Times x minus x cubed over 4. Okay, so now we've written the volume as a function of one variable, and we can now maximize that using the techniques we've learned from calculus. Okay. Okay. So, oh, I just noticed another constraint. I noticed that since the surface area is at most 108 square inches, x times x, so x times x can be no more than 108, which means that x can be no more than root 108. So in my formulation over here, there. Okay. So now that I've written it this way, writing the objective function in terms of x happens because of the constraint here. So now I can reformulate this whole optimization problem by, I can get rid of this actually, and I can change this objective. So I'm going to go ahead and do that because I want it to look really nice and neat before we do any calculus, basically. So what does our new problem look like? So we want to maximize subject to x, volume of x, which is equal to this formula. Such that, now this constraint was included when we made this, so it's kind of enforced on its own, such that 0 is less than or equal to x, which is at most square root of an 8. Okay, so now this is our problem. We've set it up, and now we can use the techniques from calculus to optimize this problem. So in particular, I need to find the critical points of that function v. So then d dx of v of x equals, take the derivative, that. Okay, so now that we have the derivative, and this is defined on, again, we have our constraints on x. So those are the only x that make sense in this problem. Okay, so now let's set this equal to 0. So then we have so then we get what? 4/3 of 27 square inches is equal to x squared, which means that there's 4 times 27, that's so look at that. 80 plus, oh, I can just divide by it, oh, I can simplify it. So yeah, so this is like 4 times 9, right? So then if we solve for x now, notice that the units work out. You take the square root of inches squared and you just get inches. And x should definitely be written in inches. So this would be, so 2 times, yeah, so it's going to be plus or minus 6 inches. But we know that our constraint on x tells us that x has to be positive. So we see that x is equal to 6 inches. Okay. So Once we have x, then we can find out what h has to be by just plugging in to this bit here. So then, what is that? 108 inches squared minus 36 inches squared. I'm keeping the units to make sure that everything aligns at the very end. If you ever get that the units don't make sense, you know you probably made a mistake somewhere in the formulation. 4 times 6 inches. So what does that become? So inches minus 36 square inches all over, what is that? So yeah, 24 inches. So the inches will, so what does this become? 108 minus 36 is, I'll just quickly do this right here, just because I'm not too quick today with mental arithmetic. So 108, 2. So I'm just going to keep on reducing down. So this is 36 over 12 inches, which finally okay. So I think that's 3 inches. Okay. So does everything work out? Let's like check to see that our area is satisfied. So we're asking the question, does area equal 6 inches squared plus 4 times 6 inches times 3 inches? So let's see. So yeah, that all adds up. So inches times inches, square inches, and all of this does indeed equal 108 square inches. So we're good. Okay. Now we do need to determine if this is if this choice of x is a maximum for that volume function, right? Which we can do using the second derivative. So let's go ahead and do that. So the prime of x is equal to, what was it over there? 27 square inches minus 6 squared. So then the double prime, that goes to 0. So then negative 3/2 of x, which is less than 0, which is good. Which means we're concave down, which implies that that this will be a local maximum. In fact, yeah, it'll be a local maximum. So that's it. So then we have, we're done. X is equal to 6 inches. And then the height is going to be 3 inches. And those are the dimensions that maximize the volume for that open face, that open box. Okay. Any questions on this problem? So really, with these applied optimization problems in the textbook, it really is a case of just taking your time to set the problem up correctly, make sure that everything is nice and neat. And then after you have the problem formulated in a neat way, and you know how your variables behave, you know the function you're supposed to be optimizing over what interval, then you do your optimization techniques, and then you determine if you find max or min, whatever the question's asking for. Okay. Okay, so let's look at another problem. Yeah, let's actually look at the problem that I discussed last time. I asked all of you to work on together over the weekend. So the question again was, so which points on the graph of y is equal to 4 minus x squared closest to the point 0.2. So that was the problem that I posed for you. So again, when I look at these problems, my very first instinct is to try to draw a picture if I can, which I definitely can for this. So what does this look like? So the intercepts are at right here, and that's more or less what the graph looks like. Okay, and then 0, 2 is like right there. And we want to know what the closest points are on that graph to that point there. Okay, so let's see if we can do this. So we need to find the function, our objective function, the thing that we're going to optimize. We need to find that first. So in order to do that, I noticed that I can make use of the distance formula in Euclidean space. So then I can say the distance between 2 points is equal to the square root of x1 minus x2 all squared plus y1 minus y2 all squared. So this will be the objective function, or the primary equation that your textbook uses. So then, well, we know one of the points is 0, 2, so we can just substitute that in. And it doesn't matter which one you substitute in for. Maybe I'll just do this. And then for my y1, I'm going to choose this equation, right? Because this equation is what gives me my y value for a given input x. So I'm going to say 4 minus x squared, and then minus 2 all squared. Okay, so x1 is just x, y1 is just the output for given x, that's there, minus 0 because that's the x value for the point, minus 2 because that's the y value for that point. All right, so let me just kind of clean this up some more. Oh, square there. So it becomes x squared, so plus right there, plus, so 4 minus 2, 2 minus x squared, all squared. So this becomes, what does this become? So plus 2, and then minus 4x squared. Plus x to the power 4, I'm pretty sure. Just gonna clean it up a little bit. So what does that become? X to the power 4 minus 3x squared plus 2. Did I do that right? Make sure my algebra is working out because I am kind of out of it today.
We got plus 4, not plus 2.
Oh, yeah, you're right. 2 times 2. Let me just make sure. So like here's my y, my x, that's good. 0 there, 2 is there, good, good. I think that's it. Okay. Now, are there any constraints on what my x can be? I guess, yeah, there really aren't any constraints on this. We just have this. Well, I suppose the inside needs to be positive, right? So then we can say that this is greater than or equal to 0, so we take in square root. I think this is looking okay. I'm kind of concerned about that 4 on the inside, that power 4, but I think this is good. So now, notice that the square root function, what does the square root function look like? It looks like this. Right? So as x is increasing, the function y is increasing. So maximizing this, right, is equivalent to maximizing the following. So we're finding the max x for this. Or if we're maximizing this function for the variable x, this is the same thing as maximizing for x the inside. It's the same, the x that maximizes this will be the same x that will maximize that. And that's because the square root function is an increasing function. As x increases, square root increases. So if we find an x that maximizes the inside, it's like the same thing as finding an x that maximizes the whole thing. Okay, so there's my objective. The inside needs to be greater than or equal to 0. I do know that though. So maybe I can come back to that in a moment just to make sure. But that's my function. So if my d of x is this, then I'm looking at my critical points. that. And if I set this equal to 0, I can divide the whole thing by 2. And then do some factoring. Like that. So then, so what are my critical points here? So x is equal to 0, and then also x is equal to plus or minus the square root of, what is that? 3/2? Yeah. So these are my critical values. Okay. So now I just need to test. I have to make sure that all of these result in this being positive, and then also the inside being positive, right? If this is because we're not taking square roots of negatives. So, and then I need to test which of these are maximums for this distance function here. So with that being said, I probably need to take the second derivative and then check these critical points, or critical numbers. And the second derivative is going to be 12x squared minus 6. Okay. So again, we're focusing in on this equation here. So then let's test out. So d double prime at 0 is equal to -6, which is less than 0. So if we're going to be concave down, which implies 0 comma d of 0 is a maximum, the local max, right? D double prime of positive root 3/2 is going to be, what is this, 12 times root 3/2 all squared minus 6. So what is that? 18 minus 6. Okay. So, all right. So this is concave up. Which implies that root 3/2 comma d of root 3/2 is a local min. Okay. And then it's the same thing. This is also going to equal d double prime of negative of root 3/2. The same thing's going to hold. So it looks like root 3. So we're trying to find the closest point, right? So this distance function here. Oh, what am I doing? I don't want max. Because we're looking for the closest point, we want the min. Okay. So yeah, probably should have caught that earlier. So these local mins here are minimization points for this, which would be minimization points for this, which means that these are the x values for which we'll minimize that, and we found our points. So what are the points? Root 3/2, comma 4 minus root 3/2 squared, because that's what our y is, right? Just plug in. So what does that become? 4 minus 3/2 is 5/2. And then the same thing will hold for the negative. So negative root 3/2, comma 5/2. So those are the points that are closest to the graph of that function. Is that what you guys got?
So I think one of the ways we tried solving it, I think Stephen got that. The other way, we didn't end up getting rid of the radical, and then that got us to plus and minus the square root of 6/2 with the same y, or 5/2, not, yeah, 5/2 is the y.
How did you get 5/2 for y? If you plugged in square root of 6 over, no, what do you have here? 6/2?
Yeah.
So just 3. Okay. Well, I'll have to look at the work you did to check that, but this should be the correct answer here.
All right.
Okay, so I'm gonna go ahead and stop this recording on optimization, and